Hi, I'm Ralph Gable, and today we're going to talk about understanding current. The most basic illustration of current is that of water flowing through a pipe. We have water in this pipe coming from our bucket above. We can see, as evidenced by our fancy smashy pressure gauge, that we have water pressure, and it is this water pressure that would drive the water through the pipe. So the water enters the pipe at the top, and that same water that enters the top ends up traveling the entire length of the tube down to the opening. So when I open this valve, the simplest explanation says this flow of water is an indication of current. This is an illustration of current. And that's kind of true, but it really doesn't tell the entire story of what really is happening with current. And you, being the inquisitive experimenter, want to know the real deal. Current is measured in amperes. So what exactly is an ampere? Well, an ampere, or current, is a measurement of the number of electrons passing a point in a conductor in 1 second. 1 ampere is 6.24 million trillion electrons passing that point here in 1 second, or 1 coulomb per second. The term ampere is named after André-Marie Ampère, a French physicist and mathematician of the 19th century. So that's what current is. But does it flow through the wire in the same kind of way that we think water flows through a tube? That's what we're going to find out. Okay, let's start with the structure of the atom. Well, the atom is made up of a nucleus which has neutrons and protons, and this is a lot like the sun in our solar system. And then spinning around this nucleus are the electrons, and these are kind of like our planets in our solar system, but think of it, our planets in our solar system are not all on one track. They're in different layers around the sun. In a similar fashion, these electrons are at different levels around this nucleus. And the outermost electrons are referred to as the valence electrons. And depending upon the material, these are the ones that are most susceptible to being displaced. And so these electrons then can be displaced from the atom and wander over and take the place of electron in another atom somewheres. But these valence electrons out here is the ones that get displaced and are the movers as far as electric current is concerned. Okay, so if current is the movement of electrons, does that mean that when we have a conductor where there is no current in that conductor, does that mean that the electrons aren't moving? Well, the answer to that question is yes and no. How is that possible? Well, like I said, remember we talked about the atom and the valence electrons can be displaced. I mentioned that the valence electron from one atom can move over and take the place of a valence electron from another atom. These electrons are wandering about inside of this conductor, joining to this atom and moving away from this other atom. And so if we were to look at this like this, like here we have this conductor, and all these little green circles are our electrons floating about. This electron might float this way, and this one will float this way, and this one will float this way, and this one will float this way, and you know, this one goes down and this one goes up. If you were to take the vector sum of all of the movement of all of the electrons in that conductor, it ends up being 0 because it's perfectly random. So this electron is moving just as far in the down direction as this one over here is moving in the up direction. So the overall movement is canceled out. This one is moving down and to the right, this one's moving up and to the left. And so there's no current, there's movement of electrons, but in no specific direction, just between one atom and the next. So what happens then when we have current? Well, now it's a little different story. Now, if we go back to our lesson on voltage, remember that an electric field exerts a force on charged particles. So here now we have an electric field because we have now put a positive over here and a negative over here. Now, these electrons in here are still doing their very random kind of movements, but what's happening now? Well, these are all negatively charged in here. And so they want to go over this way. So what that means is that this guy up here, because of this positive charge over here, he's going to want to move further this way before it hits another atom and takes the place of the valence electron. This one here, while it wants to move this way, it won't move quite as far this time. And this one will tend to move further in that direction, and this one will tend to move not as far in that direction. And so as a result, what we end up with is a general movement. If you take the sum, the vector sum of all of the movements of these electrons in here, you're going to find that they are going to be favoring this direction. So it's kind of like taking a box. Let's just suppose that we could take a box, a perfectly flat box, and set it on a vibrator table, and the vibrator table is perfectly level. Now we dump a whole bunch of marbles in there, 10, 20 of them, and turn on this vibrator that vibrates perfectly in all possible directions. Well, if we were to look down on those marbles, they're just going to they're going to be moving, but they're not really going to be moving toward one end or toward the other end. They're just going to be moving around the box. But what happens if we apply our force, in this case it would be gravity, by just tipping that box just a little bit? Same conditions, same marbles, same box, same everything, except now we're allowing gravity to exert force in a particular direction, and this box is vibrating. Now the marbles, while they're still going to be moving around in a very random fashion in this box, you're going to see the general movement of all of these electrons toward one end of the box. And as they gather at one end of the box, we take them out, put them up on the other end, and they're going to keep moving. And that's kind of the picture of how current flows through a wire, how the electrons work around and move around in a conductor under the influence of the electric field. So I have two last things that I want to address with regard to current, and I'll do that in quick succession. We have conductor versus non-conductor. The only difference between a good conductor, a not so good conductor, and an insulator or non-conductor is the availability of these electrons to be used for current. How mobile are the electrons? And those materials that hang on to their electrons really well are the insulators, and those that are more generous with their electrons are the conductors. And the more mobile the electrons are in the material, the better the conductor is. Now, conventional current versus electron or real current. When we talk about current, in general, we think about current moving from the positive terminal of a battery, for instance, through whatever circuit that we have and back to the negative terminal of the battery. But that's not really true, because real current is electron current. We already know that. It's the movement of electrons. They are the negative charged particles. And so real current is actually flowing from the negative terminal of the battery through the circuit and returning to the battery on the positive terminal. So does it really make a difference? Should we care about which one to use? And the answer is no. As long as we are absolutely consistent in the convention that we choose, it doesn't matter which way we decide current is going to flow. Whether we want to use conventional current because it makes more sense, thinking of, the water flowing downhill into the lower pond, or whether we want to be a purist and say that it's got to be the other way. It's electron current. We got to go the other way. It doesn't matter. As long as you are consistent in the convention that you choose, your calculations will all come out the same either way. So no, it doesn't really matter. So there you go. And that is all I have to say about current. Thank you so much for watching. Toodaloots.